Dario. I am a machine learning engineer for Cisco, and with is some of my colleagues at Cisco, and we work on the WebEx assistant, which is the, can I say, the Google Home or the Alexa for business that Cisco is building. And we are doing research in this domain, and we are working on it. And today we want to show some experiments we're working on, some other research where we want to take advantage of the devices that we have at Cisco. We have big screens with multiple cameras, with microphone arrays, and we wanted to create something that is even more personal, interacts in a more natural way than other devices can do nowadays.
Yeah, we, when you interact with Google Home or Alexa or Siri or whatever, we're still at the point now where you're usually doing it over voice, possibly text. But humans don't, that's not how we communicate, right? We look at each other, we gesture, we teach by showing. And so we're trying to take AI down the road of it feeling more like a normal human interaction when you are talking to it or being with it. And this, we've sort of been spurred on to do this because, like Dario said, we've got these devices with super high resolution cameras and good mic arrays. So our AIs are kind of naturally more visual and auditory than some others. And so we want to take advantage of that and make it feel more like you're talking to a person rather than just a program.
Yeah, so we took inspiration from how more or less our brain works. We have an amazing brain that seems like to have a common, just one algorithm that is very flexible. So that's how we built this. If you look at the evolution with our brain, we can see this the newer part of the brain, the neocortex, and why we have also the older part of the brains that are more suited for encoding inputs. We have eyes, the part of the eye, we encode what we see with our eyes, we encode what we thank you. Okay, testing. Good. Big home. We encode what we hear with our ears, and there is one big chunk of our brain, the neocortex, that is using one single algorithm to just process everything and make sense out of it.
Yeah, and I mean the old parts of the brain obviously are older, and they evolved early on, and so they are usually trained on a single task. So you have incoming audio, and it needs to be represented in some way that the brain can process later. And so there are particular parts of the brain that have tended to specialize in those areas. The neocortex is like an innovation, and it's mammals have them, and some other creatures don't. And because of that, we're able to do things they can't, right? And this newer part of the brain is basically a pattern recognizing layer that has essentially a single algorithm that's repeated over and over again. And so even the same parts of the brain can process different kinds of information if they need to. And if you look at this kind of slide here, there's a blind woman that's feeling a set of pinpricks on her tongue. There's a sensor there with a grid. And essentially what the camera is seeing in the glasses is translated into a set of vibrations or electrical signals on her tongue. And just like you can have a very kind of maybe 8-bit version of reality, they have a kind of maybe 9x9 version of reality. So each pinprick is like a pixel. And she's feeling on her tongue what the camera is seeing. So even though it's a feeling that's occurring, the visual part of the brain is usually processing that information. But you can even, or they have even done experiments with, say, mice, where they've, I think they destroyed the visual part of the brain, and they sent the visual signals to the auditory part of the brain, and that part was able to retune itself to understand auditory signals. Now this is just a metaphor for what we're doing, but the idea here is that we wanted to build individual senses that are taking in the input, encoding it into a kind of common hyperspace, and feeding that into a central algorithm that is doing the same kind of pattern recognition. Sorry.
Yeah, the key is flexibility, and the way we structure architecture is one major loop, like programmatically is a loop, always listening for events for these encoded inputs. So that's why the picture of this loop, that's where we put our neocortex, if you may. And then we have all the senses that encode in this hyperspace that we a common hyperspace numbers that are sent to the main loop. And you can picture this as like a central loop, and then all these senses sending in a full duplex mode back and forth signals, and we can build smarter and smarter reasoning on top of these senses.
Yeah, at every time step, basically the loop is saying, okay, what do I know? What do I know, right? And as it's doing that, it's getting inputs from all of these individual senses. And we architected this in a way where the senses can, practically run on any device anywhere in the world, and they're communicating asynchronously over a kind of eventing system. And so the main loop can be anywhere and be pulling information from a camera somewhere and a microphone somewhere else and maybe a LiDAR somewhere, whatever it is. And it's just receiving information asynchronously, figuring out at every time step, I've been given this information, what kind of higher level reasoning can I do on top of that?
Yeah, so today we're going to show step by step how we build this. So we have live demos for each one of these senses, and then a final demo we put everything together. And so we start from the ground up. What's the first simple sense we have on your board? It's a sense of hearing. And the first very simple thing we can do is just detecting whether or not something's happening. So we just built a simple ear with microphones, and it's sensitive to voice. So now as soon as we run it, I'm going to show this on a screen, and when a red dot appears, my voice is heard. Otherwise, nothing appears. So everything is live demo. Everything is running locally on our MacBook. So it takes probably a few seconds for each demo to be set up. But we wanted to build it with you guys. So now you can see there's a dot in the screen, and the microphone is there. So when I don't talk, it doesn't show. When I talk, instead, it's back. So this is the the simplest sense we can have with ears.
And if you think about a new creature has been born into the world, one of the first things they should pay attention to is noise, right? Do I hear someone talking? And naturally our brains are tuned to follow voices. So the very first thing you want is something that knows when there is talking. Okay? But that's very dumb, right? It's very simple. But part of what we're trying to do here is we're beginning to build up a set of senses. So that's just sort of number one.
Yeah, the second one is going to be object permanence. That's we can see objects, we can recognize that this thing is different from this other thing, but you also want to be able to say that this glass is the same glass now, here, and then there. So this kind of object permanence is a simple task that we build while we're babies, but we also want this in machines. It's not as simple. It's easy to do object detection at each frame, but you want to make sure that this is the same object throughout the living moment of the AI. So now we're going to show you with faces. Now it's only interested with faces.
Yeah. So it's straightforward to say I see a particular object, but even systems now are not that great at knowing it's the same thing, right? Now, when you see my hand, it's effortless for you to know it's the same hand here as it was here. That's actually not trivial for even AI algorithms. So, so the first thing we needed to do is tell it or explain to it what the same object looks like across time. So even if I go out of the picture, I can come back and it's still the same color, right? The color is denoting that it's the same face. So if Dario comes into the picture, he's got a different face, right? And you can cover your face up, and it'll go away, but when I come back, it still knows it's the same person, right? Yeah. And strangely enough, the system's already smarter than toddlers, right? Because for very young children, if you take an object and you hide that object behind a screen or something, they think the object has ceased to exist. And it's not until about the age of 3, I think, or 4, where kids are able to connect that object that went away and came back as the same one. So, yay for us. We're smarter than a 3-year-old.
Yay. We're going to get smarter and smarter throughout the demo. So the next sense we want to do is speaker recognition. As humans, we're very good at recognizing when different people are talking. I can, after talking with Will even if I just met him, I can immediately pick up his voice, how he sounds, what his accent is, his speech, and everything. So the way we did, we built these encoders, these senses that are this very sense is sensitive to how people talk. And I would be, now we're going to show that we are able to project this voice like as a sequence of numbers. I don't know how many people are technical. So in this vector space, in the hyperspace, where this sequence of numbers represent my voice, and different numbers that are close to each other represent my voice, and if they're farther away, they represent someone else's voice.
Yeah, just to explain that a bit more, the way that we were able to take a voice and create a kind of fingerprint for it is you first train on millions of voices that are not the voices you care about. You're learning how to take the incoming audio signal and turn that into a set of numbers that properly encode the semantics of the voice, so what matters about that voice. Once you're able to do that, you can take a new voice, which it's never heard before, and you're able to encode it successfully in a way that captures what's important about that voice. And then once you do that, you're able to then cluster those, right? So you can think of these as points in space, and the more I talk, what's happening is it's plotting these encodings in space. That's what the little dots are at the bottom. And right now, they just look like a big kind of universe of dots, right? That's because they're actually really close together. But that's all me talking. So if I stop talking and Dario stops talking, what should happen is that you should begin to see the clusters develop, and his separates from mine.
Yeah, so we use a very high-dimensional vector space. So we represent voices with 300 numbers. But we are just showing on a 2D plane, so we're compressing a lot. Despite that, you can see that already my voice is being projected to a different hyperspace on the right side of the screen. And this is done all unsupervised right now. So we don't want to tell what's going on, we just want to show that we make sense out of the environment. And then we will build on top of this.
Yeah, the system has never heard either of our voices before. And so it's able, you visually can look at this, and you can imagine drawing a line down the middle. And that's essentially what a lot of machine learning is drawing lines down the middle of things. And that's easy to see visually, right? And the reason why we care about doing this in an unsupervised way is we want the AI to be able to encounter new people that it's never encountered before, and still be able to do something with them, to be able to understand that they are different people, to know when one's talking versus the other, and so forth.
So now we can recognize when different people are talking, we know when they are talking, but also we want to interact with the device. We want to get its attention. And now if you think about Google Home, Alexa, Siri, you say the wake word, you say the magic word. But as humans, we have different ways to do it. If you have cameras with eyes, I can get Will's attention by saying, hey, Will, and then he turns and looks at me. So we build something like that. We build gestures.
Yeah, and so just to give some background on how that works, if you think about movement, it's essentially a set of static images across time, and so typically how you would train sequences of motion or something is you might use something like a recurrent neural network, like an LSTM, and you give it maybe the image across time. We took a different tack because the thing we have to do is get these models to run on really like kind of low-powered embedded devices often. And so we thought, well, is there a way of representing motion across time in a single image? And so what we did was we essentially smooshed movement into a single frame, and I'll show you what that looks like. Oh, is it there? So you can see our model starting up here. And if I were to, so what the system is seeing, if you were ever a kid and went to the museum, you'd see these things, right, where you play around with, you move your arms around, and it would be like in rainbow colors. It's the same principle. But what we're doing here is as you see the color decay from white to red, what you're seeing is time, right? And so this is kind of a spatiotemporal representation of motion. And so the reason why we did this is instead of giving the network a full color image, and it has to learn to ignore backgrounds and the color of our clothing, maybe our face, things like that. By giving it a simplified input, it's able to generalize a lot faster on a lot less training data. And so we're able to train on gestures with just a couple hundred examples instead of say thousands or millions or whatever. So if you were a person and a friend of yours was at the airport and you saw them, you might like wave and say hi, right? Or you might be like, go away. Or you might be like, I want number 1 or number 2, right? Or good job. So we can quickly when I want to train something like this, I'll just start making some motions. I'll record them and I'll say, okay, that was a swipe or that was a swirl or whatever it is.
Exactly. Something that learns very quickly, new gestures. We wanted to do in a few weeks of research what evolution did in a few millions of years, encoding a smart way, a very complex input source. So that's why, as Will showed, is very robust and it's able to learn new gestures, new way of communicating to the agent very quickly.
And our brains are very efficient. I mean, they run on about the power of a light bulb. I think that's true. That's kind of apocryphally true, but it's not that much power. And the brain does really smart things, like it ignores lots of input and simplifies problems. Like when you catch a ball, like a physicist or someone that's been studying calculus might invoke it to catch the ball. They might talk about movement over time and parabolas and such. But that actually is not the way our brain does it. Our brain takes the 3-dimensional movement, compresses it down to 2D, and turns this 3-dimensional movement toward you into a 2-dimensional path, which is much easier to solve, right? That now becomes straightforward geometry. And so we took inspiration from stuff like that to try to make our prediction simpler, right? Don't give the model a hard problem when you can give it an easy one.
Right. So the next probably is we can get attention. And Will knows I'm talking to him if I wave at him. But as humans, we are also more subtle than that. When I want to talk to him, I just look at him in the eyes. So we also want to capture that. We want to capture natural interaction that humans do naturally. So we work also on realizing when I'm looking at the camera, at the eyes of the agent. So we work also on some gaze detection. And that's very important for having also the natural interaction that we building step by step.
Yeah, one of the frustrating things when you're dealing with a typical assistant or a digital AI, what do we call them, the things on your counter at home, is that you tend to say, Alexa, what's the weather? Alexa, what's my, play some music. And then every time you interact with it, you have to kind of explicitly tell it something, right? And I mean, that's already very impressive, and we get bored with things pretty quickly. But it can be frustrating when you have to do it over and over again. And now both Google and Amazon are starting to allow it to listen a little bit more, to have kind of ongoing dialogue. But that is still kind of dumb in a way. And humans are very good at. Humans are very good at figuring out when you're paying attention to something. And so the first thing we tried was we made it so that our AI can respond to gesture waves, right? So it wakes up when you wake it up. So you can say something like, hey, make a phone call or whatever. And that kind of hey, is a little simpler than okay WebEx, which is our wake word, or okay Google, or whatever. And just doing that in a meeting is a lot less disruptive than saying these wake words. Okay.
Yeah. So the next is sorry for jumping ahead. We talked about gaze, so that's even more subtle, and that would be so the gesture that we experimented with our meeting environments, but that's what the devices we're building are for. So in a meeting, you can wake up the WebEx system with your hands, but for something more personal, and also if you're using a meeting room when you're alone, you can actually just count on where you're looking at. And for multiple people, if I'm looking at a device and Will is not, maybe I'm actually talking to the device. So we can use these clues to make something that is paying attention to the right thing in the right moment. So
yeah, this is basically how you teach a child something, right? The kid's looking at you, making eye contact, and you're like, now don't do that, right? So this is essentially the same idea. Instead of having to say, okay Google, or wave at it, or whatever, when you look at it, it's like, okay, you must in some way be interested in interacting with me, or why are you looking at me? Now that's not the only signal we look at, but it is kind of an interesting one. So I'll show you what that looks like. Okay, so there's the face. And so you can see it's doing the face detection, but it's also doing this additional thing where it's trying to figure out where I'm looking at it. Right now it thinks I'm paying attention to it, which I am. If I sort of look away a little bit, it kind of stops paying attention. And if I come back to it, it knows I'm looking at it again. And so, that subtle signal of are you paying attention to me can be interesting. If Dario comes in, we're both looking at it, moves away.
Two people to look at.
Yeah, and so like just we showed there, if there's two people in the camera, now it doesn't know exactly who's talking to it yet, but it's an indication that, well, I think at least two people are interested in me, and now I can use other signals that I know about to figure out which one, right? And so some of the stuff we're going to show you next is like is where we're adding additional senses to figure out, okay, I see two people, they're the same two people, I see some faces, one of them is looking at me, one's not, maybe. How do I figure out which one's actually interacting with me?
Yeah, so this comes natural that we talked about. I know when something's happening, I know when a sound is happening, I know when there's a gesture, when someone is looking at me. And we are working 2 years, 2 microphones, I would say. And because of that, we are able to recognize if something's happening to my right, my center, or my left. So because I mentioned we have microphone arrays on the devices, we want to do the same. We have microphone arrays, we know where sound comes from. So we can probably show the sound localization that we built. It's a very simple algorithm. It's a very simple concept, but that's important. Think about now the situation where we had two faces looking at the device. If I'm talking, how do we know it's actually me? We can actually use a speaker embedding, as I showed before. You can recognize my voice, or we can also use the fact that I know the sound comes from the left or from the right.
So you can't see it, but right here we have a very cheap mic array. It's just a circular board with little mics surrounding the outside, and it just is figuring out where's the sound coming from. So earlier we showed, voice activity detection, which is, do I hear a voice? And the other thing we're going to add here is, where is the voice coming from, right? So you can imagine if I see a face and I see another face, but I hear a voice coming from that direction, it's another indication of where I need to look to figure out who's trying to address me. Okay? We'll try to show that. This is a little complicated because we have a bunch of devices communicating over public Wi-Fi, so we'll see what happens. And I'll just repeat that we squeezed all these models down to run on a laptop, so this is just a CPU running these models. Typically we have GPUs and stuff, but it still works okay.
Yeah, sure.
Okay, test.
No, we didn't stop the video. So test. Okay, so I am now on the left side of the device, and you can see the red dot is following me. But if it will talks,
if I talk, it's going to bounce over here to my side. Now this seems stupid, right? It seems obvious, but just alone with the little red dot buzzing around, you now know who's talking, right? And you can imagine associating the face with that little red dot.
And it's only sound-based. There is no camera involved. There's no motion involved or face recognition. We just want to show each single sense one at a time, and then eventually we show how we put everything together.
Yeah, so I mean, this is just another dumb sense, right? And the premise we have is that if you add enough dumb things together, you get something that's smart. I don't know if that's true, but we'll find out.
So next, okay, so we showed everything, focusing. And now the next is focusing on what really matters. We have one more way to pay attention to things. It can be I follow objects, or I can hear where the sound comes from. I can look at a person interacting with me, or something even more even simpler, which is something is moving. I looking in front of me and something moves. I just look. It's very basic, but there's also a way to know if someone is talking. I'm talking, the one that moves the most, also, using my hands a lot. So that's also very simple. When I want to get my cat attention, I just do like that. The cat hears the sound, it sees my hand, boom, it moves there. So we build something that is very sensitive to motion, but something that also has some memory. Like we have some persistency in our retinas when we look at something. Like if you look at the sun, you still the image in your retina for a few seconds, unless you watch it forever. So another way is also that we have a very high resolution vision just in the center of vision, and then we have a very blurry peripheral vision. But it has a persistency. That's how we think we see very high resolution.
Yeah, so if you look here, we're both moving a little bit, and it'll decay, so whoever's moving the kind of most it will pay attention to. But it's sort of like if you look at a bright light and you can see like an afterglow of what you just saw. This has the same effect. So we essentially gave it a single focal eye, and so it has one little area that's clear and colored, and everything else is sort of blurry and gray. It's just like our eye, right? We have the rods that are on the kind of outside of the eye that see black and white, and they're good for peripheral vision, but they're kind of blurry and gray. And then we've got the cones in the center that see color, and then there's an even smaller part of that that's really clear. And so that's kind of what you're seeing here, is it's trying to figure out what should it pay attention to given some movement, right? And it's, you can imagine, like in addition to the hearing where someone's coming from, this is detecting like what interesting motion do I see, and it sort of clusters that into little blobs. Then it figures out which of those blobs is the most interesting, and it follows it.
We can probably show them together now with we have a blue and a red dot. I guess we have the screen now. So as we showed before, there is a red dot following my voice, and now we have this motion detection. And so we can show that these two inputs are going to be noisy, they're not going to be precise, but eventually we're going to use these noisy, imperfect inputs to make very careful and smart decisions on what to pay attention on.
Okay, so I'm going to start up.
Again, everything is local, so. Yeah.
Oh, there it is. Okay, so this gives you a little bit more sort of the debug view, and you can kind of correlate how it's looking. So as I move around, you can see the little red and the blue dot dancing around me, and the red dot is the speaker tracking, and the blue dot is motion. So Dario is moving a little bit. He's trying to steal my dot. We kind of fight back and forth.
But if I say hello, okay, close now.
Yeah, so it quickly can bounce back and forth and figure out who to pay attention to. And if I, wave, the blue dot is interested in my motion, but the red dot's still, coming from my mouth.
Yes, I agree.
So you can imagine if you're trying to teach an AI about a new object, like I'm going to teach you what this thing is. You can be like, hey, this is a cup, or this is Dario, right? And it's able to figure out both, who's talking, but also what you're indicating.
Right. So yeah, this is the backbone. But we want to talk about how that we combine these things together. So the very simple thing is probably to build ad hoc algorithms. So to sort of kind of hard code the neocortex, the algorithm of the neocortex. Another way is to let machine learning do its job, have multiple examples of what the right behavior can be, and then build something smart with that. Another approach we wanted to try is using reinforcement learning, something that feels more natural. Probably give me the slide I can give a better idea. Yeah, thank you. So for those who are not familiar, reinforcement learning is one of the domains, the fields in machine learning, where instead of giving for each action of the AI the right or wrong response, we let it act for a while. We let it try different actions, and then only at the end we give reward, saying good job or bad job. That feels more natural. We wanted to try to teach the AI to make the right decisions on what to do with the senses with this approach. So you can see on the left side, yes, the left side of the screen is the usual probably the usual graph you see with reinforcement learning. The environment is the world that we can see with our eyes, with our ears, microphones, and cameras, and all these senses encode the state, and they communicate the state of the world to the agent, and also they provide rewards, meaning saying good job or bad job. For example, we can tell it, you should follow faces. And when the agent is following faces, moving around and following faces, the environment can provide a feedback to that. this would allow the agent to learn something generic, something how to behave properly in different scenarios, given the goals. But also, we want to go something somehow beyond. We want to make it personal. So I put my little goal of me, where I can provide even stronger rewards when it does something unexpected, and maybe it's good. Maybe it becomes happy to see me, and then I have a way to say, oh, very good job. And this one more arrow that I want to point is also want the agent to be able to communicate to us. So we show an experiment where we encode our voices to, and we give a voice to the agent, but not a voice, not the standard voice with words, a way that we can communicate with us with a special sensor.
Yeah, so just to set this up, you've probably heard a lot of recent press about AI agents doing really well playing video games and such. And so essentially what we're trying to do is turn reality into a video game. And if you can define the rules of the game and you can define the rewards that occur when you play the game properly, then essentially the agent can train itself to behave interestingly without you actually heuristically describing it or giving it training data that explains how to do everything. You essentially just set up a game, you let the agent play it, and it learns what to do just by playing the game. And so one of the experiments we did a while back was we had an AI agent that essentially wanted your attention. And so if you think of like a dog, right? A golden retriever will try all kinds of tricks to get you to pet it or to just sort of pay attention to it. And so it doesn't just come up at you and bark. If it did that, you'd quickly just get rid of it and say, go away. So it tries more subtle things. So what we did was we gave the agent some actions. We let it beep at us. We let it buzz us on this haptic device I'll show you in a second. We let it flash at us. We let it text us different things. And initially you start up the loop, and it doesn't know anything, and it just sort of randomly is just doing things, and you just ignore it, right? Because it's like if a dog came up to you and barked and bit you and scratched you, you just ignore it, or probably kick it out the door. So we did that, and after a while I realized, okay, randomly doing all this crazy stuff doesn't work. Let me try something else. So it began to explore the space of possible options. So it might have just buzzed us or beeped at us a little bit. And when we liked what it was doing, just as a human, if we thought, well, this is a reasonable thing to do, we would look at it, and our sort of gaze was the reward to the system. And we would sort of pay attention to it when it did something good. And within 10, 15 minutes, it came up with a reasonable strategy as to how to get our attention, which was basically not to do things too much, to do a little bit of it, to know when we wanted to be left alone, but to subtly bug us once in a while to check in to see if we're ready for some attention. So it came up with a really sophisticated policy that we could, it would have been very difficult anyhow to code programmatically.
You want to show this one?
Yeah, sure. So,
yeah, you can go ahead. So we wanted to encode our voices in a meaningful way. So we showed that speaker embedding from before. We have this device with 20 little haptic feedback devices that vibrate, and that's how I encode in a 20-bit manner my voice. And you can find it, and that's what the voice, the information that the agent can provide to us. These are the actions that will send to us and get our attention, or maybe we can encode more complex inputs. We've tried with ourselves. We took place bands and talk to each other, and eventually we learn to recognize a few words, a few sounds. And this goes back to the beginning when we were talking about the neocortex.
Yeah, earlier I think I saw the slide with the blind woman with the sensor in tongue. They actually have converted sound into vibrational patterns and been able to train deaf people to hear by feeling the patterns. And if you do it enough, the same patterns, the brain is able to interpret that as words. So what you're feeling on the wrist right now is essentially encodings of the voice, my voice right now, with the speaker, being embedded in the same way you saw earlier, and being sent to that device and played on the device almost like piano keys. And it just feels like kind of noise probably right now, but if you actually do this long enough, and with maybe a little bit more detailed device, we actually had a full vest and 2 sleeves, and so we had more like 60 sensors. If you do it enough, eventually you actually can begin to decipher words. We did a simpler test where we hooked it up to our notification system. So whenever we would get a message, we would play a combination of the person's name and a little bit of the text of the message on the device. And within a day or two, we could tell who was bugging us and kind of what they were saying.
Very subtle notifications. It's not like, hey, look at my notification. It's very, you just feel it and you know it.
Right now, when you get a notification, you look at your phone and it beeps and buzzes and there's a little text or something, and it's like, the Democratic Party wants you to vote, or it's your mom saying that your house is on fire. Either one gets the exact same amount of notification space in your brain. So we thought, well, let's make this more subtle, and you can just feel the vibrations, and your brain, in a more passive way, can figure out what it should pay attention to.
And we wanted to close the loop. It's not just a loop within the machine. It's a loop between machines and men. So we want to be able to recognize how the machine is talking to us. So that's what this device is. A small experiment also to show it around. And maybe you guys can feel some noise now and learn how my voice sounds through your arm.
Yeah, I mean, I came to hate this thing because when I was training the dog, at first what he would try to do was just buzz me continuously and annoy me, and I would ignore it. It took it a little while to figure out how to send me the right kinds of messages to get me to pay attention to it.
We have one last. It's not a sense, but it's very important. It's about remembering what matters. And so far, this device is able to pay attention to feel, sense things, feel things, see things, hear things. But we want also to teach things about us. We want to make it personal, or to be able to do smart things. Like an example we'll make today is if you go to the same grocery store every day, and every time they ask you the same questions, like what's your name or where you live, you say, well, this is dumb, that's insulting. So important things about yourself that you repeat should become natural. So we wanted to build the memory with this device.
Right, and sort of going the same theme, we didn't want the system to ever have seen what you're going to tell it. Right, so with most NLP question answering kinds of systems, you tend to have the training data which has the set you're going to question ahead of time. And you sort of feed that information to the system and it encodes it in a way that's able to answer questions. We wanted to be able to learn things without ever having seen the information before, and then be able to sort of interrogate it, question it, query it using natural language without training the typical NLP stack where you have maybe intent classifiers and entity parsers and all that stuff. We wanted to simply take the information, encode it in a semantically meaningful way, without having any information about the language or anything like that, and then be able to query it afterwards.
Yeah, let's show it. So now Will is going to show like what the memory looks like before, which is totally blank, and it's going to just
let me make it blank. So
let's make it blank.
Now it's dumb. Okay, it doesn't know anything anymore. And what I'm going to do is I'm going to take some information that I pulled off a Wikipedia page about Berlin. And it can as easily read these 4 paragraphs of text or a book. So I fed it Alice in Wonderland the other day and I asked it, what happened when she drank the bottle, and it said something like she got big or whatever. So it's able to ingest lots of text and kind of answer questions about it. So it's never seen any of this information before, but it's able to encode that information and then kind of graph it in its brain. And each of these dots is a sentence. We're showing the kind of grammatical structure, that's what you're seeing, but that's just used kind of influence how we encode it. But if you've recently, you've probably heard about, there's been a lot of advances in being able to encode textual information. Word embeddings are, that's so 3 or 4 years ago. Now it's sentence embeddings and thought vectors. But the basic premise is that you learn how to, once again, encode text in a way that preserves the meaning. So if if you ever studied philosophy, you have a sentence, which is the kind of textual representation of an idea, but then you have the proposition, which is the meaning behind the sentence, right? And you know, a sentence like the dog is in the barn and a picture of a dog in a barn both have the same proposition right behind them. And so what you're trying to capture is the semantics behind the idea. And if you can successfully do that, you can map these ideas into this higher dimensional space, and you can query it. Now this is this is a 2D representation, but these are actually usually in 300 or 500 or 1,000 dimensions, and so we're squeezing it down into 2 to represent it. But the closeness of the dots represents how close they are semantically. Like 2 sentences like the dog ran down the road and the cat crossed the street are semantically very close to each other. They would be near each other in the graph, and some sentence about a doctor or whatever would be farther away. So I haven't shown you what we can do with this. So I put that in its brain. Now we can ask it some questions, like what is the largest city in Germany? And it's able to tell us that's Berlin, and it has some, it kind of also can tell us which concepts we thought were similar to the one you typed in. But we can ask it the harder question. I don't know. What was the capital of the Weimar Republic in 1920? So it's able to answer the question. And there's subtle things like, I asked it about 1920, but 1919 is kind of close to that. And just semantically, they're similar. So it's able to kind of do some subtle reasoning like that. So it's able to take concepts that are similar and know that sentences that might look different textually, and if you did pure kind of tokenization and looked at text, you might think they were totally different sentences. If you look at them semantically, they actually look pretty similar.
So now, I guess, if you can do this with Wikipedia or any unstructured text, we want to do it with our information, with what matters for us. So now we want to put everything together, all the senses and the memory, the fact that you can recognize my voice, my face, where things, what are the things that are most important that are happening right now, and we can teach it in real time. We can make the agent being bored right now being super dumb, but having these senses, these past senses, and interact with it and teach it just in front of you guys right now.
Okay, so this is complicated. So let me just try to set this up here. So we have what I'm doing right now is since there's 2 of us, we're actually going to have like 2 brains, and so this is actually part of the same giant brain, but they're going to be in different domains. What should happen? I don't know if we'll see it on here or not, but you should see information pop up. On the left, I think is me, and on the right is Dario. Let me switch those, just because we're on those sides. And so as we teach the system, these should get populated. And so the idea here, just to set this up a little bit, is the system is going to be born when I hit run. It's completely dumb. It's never seen our faces, never heard our voices, doesn't know anything about us. And it's going to learn our names, learn our faces and voices, and then we're going to teach it facts about ourselves. It's going to be able to answer the questions about those facts just for the person that asks. So if I teach it something, it's going to learn it and tell it back to me and so forth.
Yeah, no spoilers. Let's just show it.
Well, this is in case it doesn't work. So.
Right. It's gonna work. So there are multiple senses. So everything is in a different process, running, communicating with each other. So we need to start them all up together. And again, everything is local. The only thing that is not local, just to say it, is the speech recognition. We are sending the audio getting back the text. Otherwise, everything is all the intelligence, all the understanding of the senses, the sound localization, and the speaker embeddings, sound motion, everything is running locally on the CPU of this Mac. But together with the memory, even the understanding what I'm saying, structuring the memory, parsing the sentences, and make sense out of it, and responding, everything is local.
Okay, let me see if I can kind of get all this on the screen here. Okay, so just to set this up a bit. So what's happening is the system is trying to figure out, okay, what does it see? It knows it sees a face, but it doesn't know who this face is. It wants to learn about me. So the first thing I'm going to do is I'm going to teach it who I am, and then I'm going to have it remember some things about me. Okay. Let's see. Who am I?
I'm not sure yet.
My name is Will.
Hi, Will.
What's my name?
You are Will.
Let's see. So I'm going to teach it something, and right now it's listening to me, but it's ignoring most of the things I'm saying because it doesn't know anything about what I'm saying. So it's actually listening and figuring out, is this interesting? But just like with the visual stuff, textually, it's like, well, I don't know anything about that, so I'm just ignoring Will. But if I say something it might know about, or ask it a question that makes it, regurgitate some information, it will begin to respond to me. What's my favorite color?
I'm not sure about that.
My favorite color is blue. My favorite color is blue. Oh, sorry, I have to tell it to remember. It's like, oh, I don't care about that, Will. Let me tell it. Sorry. Remember that my favorite color is blue.
Okay, I'll remember that.
And you saw the fact pop up here in its brain, so now it knows about my favorite color. What's my favorite color?
You don't. Your favorite color is blue.
Okay, maybe it captured a little bit too much text there. Forget about my favorite color.
Okay, I've forgotten that.
Remember that my favorite food is pizza.
Okay, I'll remember that.
What kind of food do I like to eat?
I don't know.
Oh, you know. What kind of food do I like to eat? Do I like pizza? Just one answer. Who am I? I think she stopped listening to us.
Google is hard.
That's Google's fault, sorry.
We're relying on the speech recognition.
We're trying to see if it's checked.
Okay. So now you can. What's my name?
I'm not sure yet.
Okay. My name is Dario. My name is Dario.
Hi, Dario.
Okay.
Okay, so now it's learned both our faces, and it knows we're different people. And even if I kind of leave, come back, oh, still will. So it's learned about my face, not just that it's that box, right? And it's trying to figure out, okay, what do I do? It's like looking at both of us, here's my voice, doesn't know what to do. We're really confusing it right now.
Do something maybe? Like, remember that I left the keys on the table. Remember that I left the keys on the table.
Okay, I'll remember that.
Doesn't feel useful maybe? In a month I can come back and ask, oh wait, maybe you can see me looking for something, can suggest it. You can ask it, but it's not going to know.
If I ask it, it shouldn't tell me. Where are my keys?
I'm not sure about that.
Where are my keys? Where are my keys? You can do this. Where are my keys? Is it my accent or something?
I'm not sure about that.
Okay, I can confirm it is the Wi-Fi Google ASR. But let's try it again.
Okay.
I don't know.
Yeah, it's like super slow. Where are my keys?
I'm not sure about that.
Oh, come on, you know that. Where are my keys?
I'm not sure about that.
Okay,
Let's just read it.
okay. Remember that my keys are on the table.
Okay, I'll remember that.
Where are my keys?
Your keys are on the table.
Yay!
All right, and you can see there in the brain, that's kind of some stuff it's learned there. And that persists, right? So the next time we come around and ask it some more questions, it'll actually still retain that. So you can imagine over time, a system like this could kind of learn about you, learn your face and your voice, learn some facts about you, and even kind of more optimistically, if you interacted with something over the course of your life, maybe at some point it could actually act as a representative. So you die and your kids want to know about what happened when you were in your 20s, they can ask it, right? Because you would have told it. How did you feel on your birthday when you got the new car or whatever? And so you can sort of talk to your children from the grave. But that's a weird
that's a weird concept.
But in the immediate term, you can imagine this might be useful just to learn things that you need.
Yeah, also, as we mentioned, it's not just concepts are not just coming from words or sentences, also comes from actions or things we do or things we see. So we can, if we give proper cameras, eyes, you can learn about ourselves by just watching us, watching our actions and make sense out of it. I can ask what Will was doing yesterday if Will was in front of the system. We just don't, that's how we can encapsulate ourselves and ask questions about ourselves, not just by actively teaching it, but also by just using it. Yeah.
Okay, I think that's all. Thank you.
You can ask questions if you want. We have time for that.
With the sound recognition, how sensitive would you say your mics currently are, or how smart is the AI? Because it seems like this system is designed for a business setting, but if you're in, say, a personal setting, say, such as in a bar, for example, there's a lot of ambient noise. Will it be able to pick your voice?
Good question. So for now, the devices we have are for business settings, so it's very quiet usually. But there are multiple people talking, that's true. But there is a set amount of background noise. We can see it, there's a lot of research done in very complex scenarios. The cocktail party scenario, multiple people are talking. So for now, it wouldn't work well. Also, what helps a lot is having multiple microphones that can focus on one area, and that's what I do when I just come closer to you, I focus on you. Also, we can look into lip reading. If I want to understand what you're saying, also look at your lips, right? So we don't want to solve problems only using one sense. We want to solve audio problems with vision. Same. So if I'm talking, you can also do sort of a speaker recognition, speaker detection without microphones. Now you can guess it's me talking. So we can, instead of using just technology or microphones, we can also leverage other senses to make the right decisions or to do the right transcriptions, for example.
I think we're also thinking that that the senses can be bad. Like if you were looking down a dark alleyway, you might see a shape and you might think it's a friend of yours, but you're not sure visually, right? So you can think of it as like a bad signal. But their gait is similar to your friends, and maybe you hear them speak a little bit. And so you put together all these kind of noisy, poor signals to make a higher, a better prediction than you could have from any one of them.
Excellent presentation and demonstration. I have two main questions, with the first question having sub-questions. The first question is, what is the current limitation right now that the programs and the entire thing is suffering in terms of, is it software limitation or hardware limitation now? And then the sub-questions will be in 5 years, 10 years, and 20 years.
That's both?
Yes, both. This is like actual research for us, so it's all prototyping for now, what we're showing to you guys, and it's all compressed now. So it's hardware limitation because we're trying to make it run on limited, computationally limited devices, and software because we are discovering more and more techniques to solve problems. The reinforcement learning idea is something very new that we've been trying to use, for example. So what we see in 5, 10, 15 years is if I die, you can talk to it, and it's going to respond for me, hopefully.
Yeah, I mean, the hardware is getting better and better in some ways. I would say more quickly, but the software is developing, but it feels like we're getting to butt up against some ceilings in terms of some limitations in our current machine learning approaches. And so like no matter how well you can encode text and semantically represented, it still doesn't seem to be getting us to the point where they understand, or these machines understand the way we do. So there's simple things that can trick up a system like this. Basic things like negation and transitivity and various forms of logical reasoning are really hard still for them to do. And there have been people doing good work on data sets like that, but I'd still say it's beyond state of the art to be able to reason like we do. So I think that's the hardest problem is not to recognize a cat, but why is there a cat here? What is a cat? Is that your cat? I mean, there's a whole bunch of kind of contextual questions that we're kind of really far from understanding, I think.
Follow up?
My second question is, I guess, from what you showed us today, it's evident that there's layers upon layers of different interfaces and analysis going on. I'm just curious about how are you able to overcome the black box problem in terms of determining what's going on ultimately down the line, and then being able to diagnose what's went wrong, or if it was intentionally went wrong. It's the whole area of the computer that purposely fails the tonal test.
Oh, that's funny.
Well, one thing I can say is one way for us, at least, to overcome the I don't know what's going on, is to be very smart in encoding the senses. So to have something very simple to analyze, make the main loop as simple as possible, so that when we provide these encoded senses, everything is presented in a very simple way. And so when something fails in the main loop making reasoning, it can be simple heuristics. And we want to use machine learning, of course, because it's magic sometimes, but at the same time, if you can avoid it, for the black box of problems sometimes, you want to just have simple heuristics. And the machine learning approach is what we're using before. The evolution of senses through millions of years is what we use for encoding inputs. So that's one way to have simple heuristics. Otherwise, I don't know, using black box is a problem. Using reinforcement learning is still a black box. I have this neural network doing decisions for me. Hopefully you run enough tests.
I mean, it's a black box in the same way that you're a black box.
I
don't know why you do what you do, and even I have kids and I try to train them to do things. I don't know why they do what they do. Try to get them to do something, but maybe they do, maybe they don't. So we might have to live with a certain amount of that. I mean, if you think about like an air traffic controller, right? You have a couple of planes on the screen, you can keep track of a couple of variables, right? When you've got a million of them, suddenly you just give up. And you're like, well, I'll just see what happens. But in some ways, if you follow the model of the neocortex, it's the same variable, well, not the same, but it's the same pattern recognized, repeated over and over again. So there's a kind of logic to it in the sense that, yes, there's lots of complexity, but the complexity arises from a simple thing being repeated and combined. You can get very complex gameplay from a couple of rules, right? So that there's some comfort in that, maybe, that the actual underlying algorithm is simple, but when you put it in such complex systems, they become inscrutable.
With regards to the black box, have you guys heard of Optimizing Mind?
Optimizing Mind?
Mind, yeah, it's a startup. We actually met the founder yesterday. And he sort of claims that he's figured out a revolutionary way to know why your AI is behaving in a certain way. So that sort of solves the black box situation, doesn't it?
Yeah, I mean, that would solve everyone's black box problem, right? So I would like to check it out. Also I heard that other ways to solve the black box problem is while you're training the AI to do something, you're also training to explain to you why you made certain decisions. There's also this sort of approach. Like you ask your kid, why are you doing that? So I don't know this approach from this startup, of course, but there are different ways to overcome the black box problem. Also, sometimes you also need to say, okay, I can't know it as much. But I like to, what's the name again?
No, Optimizing Mind.
Optimizing Mind. Okay, thank you.
more questions? Yeah, but what's a black box?
It's just something you can't look into, right? So there's stuff going on in the box. There's decisions being made in there. You don't know why they're being made. You're just handed an answer. Does that make sense?
No.
It's like there's a box on the table, and you have some input. You put it in the box. And you come around the other side, and you take it out, and it has an answer. And it's the right answer, but you don't know how it made the choice.
Okay.
So that's, we're talking about deep neural networks. We train them, we have these millions of inputs, and we tell them the right answer. And there are millions of parameters that are automatically tuned. And it's so complex, we can't understand why, when I provide a picture of a cat, actually it tells me it's a cat.
Okay.
So that's a black spot. And if it's a cat, it's fine. But if you want to have it in a self-driving car, and you want to decide why did it stop at this traffic light, or why did it go without stopping, you want to understand why. It's important to understand why. And if it's just millions of parameters, that's a black box. You don't know why things happen. It can be dangerous. You want to know why. So that's a black box.
Okay.
We don't even know why we do things, right? There's been experiments to show that a lot of times when we think we made a decision, our brains actually made the decision a few milliseconds before that, and they informed our consciousness that that's what it was going to do, but it feels like we decided it. And if you ask someone, why did you do that, they'll come up with a story which sounds plausible, but the science is showing us that that story has nothing to do with why they chose it. So, we might just have to kind of, get used to it.